Hello, in this video we're going to look at Lagrange multipliers. First of all, what are Lagrange multipliers? Lagrange multipliers it's a tool that we use to go through and solve optimization problems. So let's just jump right into the technique that we use. So the technique is that so suppose we have a goal of finding a maximum or minimum with a constraint. All right, so let's say that the function that we're maximizing or minimizing is f of xy. So we have z equals f of xy. This is the function that we're maximizing or minimizing. And then we have a constraint, and the constraint is given by the equation g of xy equals k. So the way that the constraint works is that the points that end up being the solutions to the problem, they have to satisfy the constraint. So if this were 10 and the function were x squared plus y squared, then you could have x is 1, y is 9. You could have x is the square root of 2, y is the square root of 8. You'd have to have the combinations that end up producing 10 are the only things that can actually answer the question. So you can't pick something that maximizes or minimizes f but doesn't satisfy the constraint. The constraint has to be satisfied. It's a constraint, it's a limitation that is placed upon the solutions. Okay, so the method itself is we go through and we find, hold on, let me actually write this. Find all the points that satisfy the following. We have gradient of f equals lambda gradient of g, and g of xy equals k. Okay, so you're going to find all the points that satisfy this. That's step 1. And then step 2, you are going to evaluate the points from step 1 in the function f, and the biggest is going to be the maximum value subject to the constraint, and the smallest will be the minimum. And that concludes the method right there. All right. So what are Lagrange multipliers? They're optimization problems. And so what technique are used to solve Lagrange multipliers? Well, so first you have to have kind of the goal. And the goal is to maximize or minimize subject to a constraint, which we described here. And then the method itself that we use to solve it is you find all the points that satisfy this. All right. And we're going to talk about this. So if you're looking at this and you're like, what is that? We'll talk about it. And then step 2, you're going to go through and evaluate all the points from step 1. And the largest is the max and the smallest is the min. Okay. What is this? All right, let's talk about it. So what the solution to this this technique, the way that this technique works is it focuses on level curves, and it uses level curves to go through and solve it. Okay, so you'll notice g of xy is already in the form of a level curve. I guess if you recall level curves from earlier in an earlier video. It's not obvious that this is in the form of a level curves, but we'll talk about it more and I'll explain that it actually is as well. All right, so the idea is that suppose you've got some level curves. So I'm going to go through and draw you a picture of some level curves, right? So let's say we've got, so that's, I'll label at the end, right? So there's a level curve. We've got another level curve. And then inside there, we've got another level curve and another level curve. So these are just a bunch of level curves. What these represent is they're level curves for f. All right, for f, the thing that we're maximizing or minimizing. That's what they represent. They're level curves for f. So we're just going to pick some hypothetical values here. So we'll say this is where f of xy equals 10. We'll say we'll use 20 for this one. We'll use 30 for this one. I don't know. Let's see where we can put it. 30. I should have drawn it a little bit bigger. And then we'll use 40 for this one. All right, so we've got 10 for this outer level curve, 20, 30, and 40. Okay. Now, on top of this, we're going to graph our level curve for g. Right, so g of xy equals k. That's our constraint. We're going to graph that on top of it. Let's use a different color maybe to help differentiate. All right. Let's see if I can get this picture to match with the drawing I did in my notes. So should look something like that. Like that. And like that. Just pretend this little piece like that. Smooth that out. Okay, so it looks like that. So what this method suggests, and I'm going to explain it in more depth, is it suggests that the only points where we could have maximum or minimum values with g of xy equals k, and where we're maximizing or minimizing f of xy, the only places where we could have max or mins are here, 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 and here. All right, those are the only places that will end up satisfying this. So this thing, this construct here, if you go through and you find all the points that satisfied, what are those points going to be in this particular picture that I drew? It's going to be here, 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 and here. All right, so I'm going to explain why that is, but just one step at a time. All right, so when you go through and you solve a Lagrange multiplier problem, you're going through and you're finding these types of points in the problem. All right, so what are these types of points? How do I tell these 4 points just by looking at the picture? All right, well, there are two requirements in the Lagrange multiplier to satisfy. you've got this requirement and this requirement. Let's start with the constraint first. All right, so two things that need to be satisfied. All right, to be a Lagrange multiplier point. I made up that name. I'm not sure that they're called Lagrange multiplier points, but that's what we're going to call them. All right, so one, the constraint. So first, what I'm looking at when I'm looking at this picture is I'm looking for points that lie on the red line or the red curve. So the red curve needs to be satisfied. The constraint needs to be satisfied. You can't look over here and say, why can't this point be a Lagrange point? Because it's not on the red curve. What about this point? No. All right, the constraint must be satisfied. All right, so the points must lie on the constraint. All right, so so as soon as you look at a picture like this and you're looking for these Lagrange points, the points that could be maximums or minimums, the points that satisfy step one, finding all the points that satisfy. First, you look for the constraint. What do you look for next? What's the second thing that I can see that enables me to identify where the Lagrange points are? The two curves need to be tangent. Let's actually put it this way. The level curves need to be tangent. So when I look at this, I see that this spot, the red curve here is just touching the red level curve is just touching the black level curve. So this is a point, this is a potential Lagrange point. Here, they're just touching, so they're tangent. Here, they're just touching, so they're tangent. And here, they're just touching, so they're tangent. So that's the second part. That's the gradient of f equals lambda gradient of g. This means this. They mean the same thing. Now, that's not obvious. I'm going to explain why that is. But first of all, the first thing is what this means, and it means the level curves need to be tangent. So as soon as I look at this picture, the two things that I identify, you help me to identify these Lagrange points is the red curve. So my eyes are just going along the red curve, and then I'm finding the places where the red curve is tangent to a black level curve that I've drawn. And so those are the four places where it's tangent. And so those are the four places where we could have maximums or minimums. Okay, so this is there's a lot to unwrap here. So first of all, I think the constraint, that's easy to understand. How does this get you this? All right, so let's talk about that. And then after we talk about that, after I prove to you that this does mean the same thing as this, then we still need to talk about why this actually works. So none of this is really we haven't really gotten into the meat of why this works. We're just explaining the technique, really. All right, so how does this imply this? All right, let's just go off to the side here. So we've got gradient of f equals lambda gradient of g. All right, what is gradient of f? All right, it's a vector. What is gradient of g? It's a vector. You have this lambda here. So what the lambda represents just represents the fact that that these vectors are scalar multiples of each other. So we talked earlier in the semester about when vectors are scalar multiples of each other. So what this means is that gradient of f and gradient of g are parallel. So if you want to list some more facts here, this is the same thing as saying gradient of f and gradient of g are parallel. Okay, the next fact, right? So that's fact one. The next fact, well, what does it mean? What does the gradient tell you about a level curve? Well, a few videos ago, we said that the gradient of the function that defines a level curve is going to be orthogonal to the level curve. All right, so gradient of f is orthogonal to f of xy equals, whatever. Let's not, I was about to use k. Let's not use k because we're going to use k we're using k for g. So we'll say L. And gradient of g is orthogonal to g of xy equals k. All right, so step one, it's saying that the gradients are parallel. That's what this statement says. Step two says that the the gradient is orthogonal to a level curve. All right, so if you put those two together, step three, it's saying that the vector that is the vectors that are orthogonal need to be parallel. So vectors orthogonal to the level curves need to be parallel. All right, does that make sense? So if we have gradient of f is orthogonal to f, and gradient of g is orthogonal to g, and gradient of f needs to be parallel to gradient g, then the vectors that are orthogonal need to be parallel. All right, so how does that turn into the vectors need to be tangent? Well, it just comes from a picture, right? So if I go through and we draw a picture, let's say we have a place where the curves just intercept just like that. Okay, so right, so if we were to go through and put the gradient vectors on here, so let's suppose this one here is f of xy equals L. And this one here is g of xy equals k. That's that one. All right, so what do the gradient vectors look like? So this is going to be gradient of f, looks like that. There it looks like that. Here it looks like that. And if we go through and draw gradient vectors for g, here it looks like that, looks like that. When it gets to right here, it looks like that, like that, like that. And so you can see where they were tangent, we ended up with parallel vectors. Now, the one issue about that picture is that I drew them as being parallel, as being tangent, and then showed that you end up with parallel vectors when they're tangent. What if they're not tangent? All right, well, in that case, you'd have not tangent. This would be a case where you're not tangent. So you have f of xy equal L. You have g of xy equal k, right? And then what's going to happen here? Here are the gradients. If they're right, so the gradients can't be parallel unless they're tangent, right? So either the curves intersect at a place where they're not tangent, in which case you have vectors that could not possibly be parallel, or they intersect at a place that is tangent and you can see that they are parallel. So those are the only two possibilities. Either they intersect at a place where they're not tangent and then they can't possibly be equal, or they intersect at a place where they are tangent and you can see that that ends up pulling that out, right? And so this requirement that gradient of f equals lambda gradient of g turns into this, which turns into this. And so that's what this requirement is it's basically saying identify the places where the two vectors, where the two level curves are going to be tangent to each other. And those are going to be the places where you could have potential maxes or mins. All right. So let's just recap so that I make sure that I'm not getting lost myself here, right? So when you go through and you solve a Lagrange multiplier problem, you find the points that satisfy this. What are the points that satisfy this? They're the points that are on the constraint and where the level curves are tangent. That's those 4 points in the picture. Why is this? It's because of this. It's the translation of this. And to go through, it's the translation of gradient of f equals gradient lambda gradient of g. And if you take gradient of f gradient lambda g, you can go through and you can kind of follow the logic that ends up producing the fact that the points are going to be tangent. Now, so all of that is just kind of building. So we still haven't built to the why. That's really just explaining what the technique does. Why does this technique work? Why is it that the level curves need to be tangent to be maximums or minimums? Ooh, whoops, I forgot a detail. Yeah, hold on here. Let me add just this is kind of a detail, but it is a detail that is going to come up in a few minutes that I almost forgot. And that is that this is all true. Everything that I said here is true, assuming that lambda is not equal to 0. All right, lambda can be 0, in which case you get gradient of f equals 0. Now that could also be a max or a min. And I'll talk about more of that in a second. So there's kind of a second case. This is the interesting case. The non-interesting case is if lambda equals 0, and then because of that, you get gradient of f equals 0. And we'll talk about that. That could also produce a max or a min, but that's really, really rare, very unusual to have that happen. You probably won't find any cases like that in the homework. This is the case that happens the vast majority of the time. But I'll discuss this briefly just for completeness. All right, so why is it that these requirements end up producing maximums or minimums? All right, let's go through and break this down into the two cases. We have the tangent case. We have the not tangent case. And the idea is to show the tangent case ends up potentially producing maximums or minimum values. The not tangent case could not possibly produce maximums or minimums. All right, so can we go through and show that? Well, let's go through and draw the two pictures. So here's our function f of xy. And I'm just going to give this, I'm actually picking a number here just to make it a little easier to wrap our minds around it. So let's call this 10. And then we're going to have g of xy, which just brushes up against the curve. All right, use your imagination. Those are supposed to be touching. And g of xy equals k. That's our constraint. All right, and let's draw a non-tangent picture. So suppose we have the same f of xy equals 10. And then we have, here's g of xy, right? So it's not tangent, just cuts right through. All right. So the idea is that if the way to think about it, or one way to think about it, is that if this is f of xy equals 10, typically level curves for functions are going to be parallel to each other to some degree, right? So if I were to go through and draw a level curve for f of xy equals 9 or f of y equals 10, what would those look like? So it'd probably look, like, hold on, let me try that one again. So this maybe is f of xy equals 9. And then over here is f of xy equals 11. Okay. If you think about like you're walking along the constraint, right? So visualize yourself walking along the constraint, right? If this is the place where all of the points are 9, right? Then, and you're walking along, then why couldn't you just draw another level curve, right? So you're walking along, this is where the points are at 9. So if you're not at 9 yet, then you're either above 9 or you're below 9. Now, based on the way I've drawn this, you could think of it like here I'm at 8, here I'm at 9. Why couldn't I just, if it's not tangent, why couldn't I just draw another curve and another curve and another curve? So why couldn't I draw a curve here that would represent 9.5? Why couldn't I draw a curve here that's at 9.8? if it's not tangent, why couldn't I just keep drawing curves, that represent heights that I'm passing through as I'm, climbing upward, right? Until you get to this point here where they're just tangent. At that point, you can't draw another curve. I can't draw another curve out here because I'm out of room. Like you just kind of run out of room. So if you think about it, like there's like level curves are all tangent to each other. Sorry, they're all parallel to each other the way that I've drawn them, from 9 to 10 to 11. Then the place where they're tangent is the place where you kind of run out of room to draw an additional level curve. All right, so that's kind of one explanation for it, is that if they're not tangent like here, if this is all the places where they're 9, then clearly they're not 9 where I'm walking. So it has to be that I'm below 9 on one side and then above 9 on the other. So that can't possibly be a maximum, right? I guess maybe not 10 because we said 10 was over here, but we could say that's 9. You're at 9.1 over on this side. Right? And so that just kind of gives you some idea that if there's room to draw another level curve, then clearly that can't be the maximum because you could just draw another curve that's going to have a higher output until you get to a spot that's tangent. Now here you can't, since you're just touching it and turning back, you can't draw another level curve. So you just kind of run out of space. And that's somewhat the same explanation in our not tangent picture. I just kind of have tied the two together, right? So if you're looking for a place where there's a maximum or minimum, right? And here we have a value of 10. Well, then I could draw another curve here and that could be 11. And I could draw another curve here and that could be 12. Wouldn't 12 be the better place to look to see if there's a maximum or minimum? And so the place where they're tangent is just going to be the place where you run out of space to draw another level curve. So if you could draw, basically what I'm saying is that if you could draw a curve that's a secant line that cuts through, then you could always just draw another secant line past that and another secant line until you get to the point that's tangent, and then you can't draw another tangent line, right? Why couldn't I draw another? Could I draw a secant line there if I draw a line like that? No, because the point is to draw the curve that's at a height of that's at the f of xy value here at this point. And so if 12 is the f of xy value, then 12 can't be this way because 12 goes this way. So that's kind of the simpler explanation, is that if you have a place where the two lines are secant like that, where one cuts through the other, then you can always go through and draw another secant line past that. And you can just keep doing that until they're tangent. That's the simpler explanation. I also find it to be the less satisfying explanation. So I'm going to show you another explanation that I actually like better, but this one is just, I think it's a little easier to wrap your mind around, whereas the one that I'm going to draw you maybe is a little bit more complicated. All right, so the idea is, for this second explanation, this is the one that I like better. So we're going to go through and say, since the gradient of f is not equal to 0, which we're going to come back to, that tells you that f of xy equals k, or we're using L, sorry, f of xy equals L is not a peak. So it's not a peak or a valley. All right, so the level curve that we have, so let's just go back to this picture, because so the level curve that we have, f of xy, all right, that's not going to represent, that doesn't represent a peak or a valley here or here, okay, because we're assuming that the gradient of f is not equal to 0. We're assuming that in this equation that lambda is not equal to 0, and we're actually finding a place where the two curves are tangent. Okay, so if the f of xy is not a peak or a valley, that means you could think of it as like the side of a hill, right? So if you imagine a side of a hill, so let's say we've got, here's a hill, right? I'm not going to draw the bottom part here because it's just going to make the picture messier. So here's a hill, there's the top of the hill, that line there. All right, so what we're saying is that f of xy equals L is not the top of the hill. So it's the side of the hill, and since f of xy equals L is the same, it represents the side of the hill that's at the same height. So if you were walking along the side of the hill, and the height does not change, then that's our f of xy equals L. Right? Okay, so this is f of xy. Since gradient of f is not equal to 0, we know that we're not talking about the top of the hill here. We're talking about the side of the hill. And in particular, a level curve is going to be the side of the hill that's all at the same height. Now, if the two are tangent, if G is going to be tangent to this, so now G, if you imagine it in, I'm drawing in 3 dimensions. So if you imagine G is just meandering along the hillside. So what it's saying is that if G and F are tangent, then the picture looks like one of the following. It looks like either this, or it looks like you can imagine you climb over the hill and it looks like that. All right, so you have one of those 2 possibilities. So you imagine you're walking along the constraint, and as you walk along, you get to this point and then you turn back. So that point would be the maximum point that you reached on the hill. Right, so if we label the height here, this is what I did in my notes. Let me see if this makes it clear. So the height here is L. The height here is L. The height here is L. Clearly, you're below L here. So you're climbing up the side of the hill. You get to the place where the 2 curves are tangent, where they just touch, and then you turn back and you start walking back down the hill. So clearly, L is going to be the maximum point that you reached on the hill. Right, in this case. Now, in the case where you climbed up over the hillside and then you started going down the hill, clearly you were above L, and then you were declining and walking downward until you just touched L, and then you turned and started going back up again. And so in this case, the top case, L is the min. Right, and so that's the idea that's represented by the place where the 2 curves are tangent. Is it's the place where if you were going up the hill and then you reach the point where you have the level curve for F, and then you stopped and then turned back, so that could be the maximum place that you reached on the side of the hill. Okay, so this requirement here is telling you where did you reach the maximum point on the side of the hill before turning back. Where did you have this happen? Now, let me just draw you a second picture to illustrate this situation where they're not tangent. So suppose you've got your hillside. Here's the top. You've got L. F of xy equals L. It's all at the same height. And now if they're not tangent, what happens to curve G? If they're not tangent, you're going up the hill, you pass right through. Could this point be a maximum? No, it couldn't. You walked right through it. On one side of here, you're below L. You're less than L. Here, you're greater than L. So when you hit a height of L, that height is of no consequence. Clearly, that couldn't be the maximum point that you hit. So if you just pass right through, like if you're secant, then you're still climbing. That can't be the maximum. The maximum can be where the 2 curves are tangent, but the maximum cannot be where the 2 curves just intersect. Now, to tie it into this earlier example, if you stopped and then turned back, the level curve that went through there, that could be where the maximum was. So if you drew a second level curve here at f of xy equals m, that one could have been the maximum. But where the two just intersect, that can't be the maximum value that you end up getting, right? And so this cannot be the max. And you could draw a corresponding picture where you come over the hillside and then are walking downward where it could not be the min. But that's the idea. So it's one of these two explanations you could use. So this one basically says that where they're tangent, that's the last curve you possibly can. You couldn't draw another curve past that. And so that requirement, that's what you need to have to have a maximum, is to have that final place, the furthest out level curve that would intersect G. And that's because it's kind of saying the same thing. And then here's the two pictures that tie in with each of them, trying to explain why this one, in a 3D sense, could be a maximum. It's the top point that you reach on the hillside, and this is the bottom point. Now, let me just briefly talk about gradient of f equals 0, because that's just going to be really obvious, right? If you have the gradient of f equal to 0, then here's your hillside. Right? Here's your hillside, and then here's the point where gradient of f equals 0. And then in that case, here's your constraint, g of xy equals k. I'll use blue again. So you're actually walking up the hillside, and then you go through the peak. Clearly, at the peak of the hill, that would be a maximum or minimum, for the curve. Right, so you notice I didn't draw a red curve. That's because there is no red curve. Gradient of f equals 0 is going to be a point, not a curve. And so if you do find a point where the gradient of f equals 0, then that point is going to be, it's going to be a local max, local min, and that is clearly going to be a possible max min. Okay, anyway, all this is an attempt to try and explain all this, the theory behind Lagrange multipliers, why they work, what this means. It means that the two curves are tangent. Why the curves need to be tangent, I gave my best shot in terms of explaining it here. I think the second explanation is better than the first one, but those are the idea. That's the idea. You're looking for places where the curves are tangent. Let's just go through and solve them. That's probably what you care most about, is actually doing examples and seeing how to do potential homework problems. All right, so suppose we have f of xy equals 3x plus y, and we have x squared plus y squared equals 10 is the constraint. All right, so the first thing you want to do, take the constraint, set equal to g of xy. Step 2, you want to calculate the gradients. Gradient of f, derivative of this with respect to x, we're going to get 3. Derivative of this with respect to y, we're going to get 1. All right, you take the derivative with respect to x times I plus the derivative with respect to y times j. Then take the gradient of g, derivative of this with respect to x times I, derivative of this with respect to y times j. All right, next, once you've got your gradients, you're going to go through and set them equal with a lambda offset. So effectively, what that's going to do is it's going to set the partials with respect to x equal and the partials with respect to y equal with a lambda offset. All right, so you're going to have 3 equals 2x lambda, and then 1 equals 2y lambda. All right, and then finally, you're going to take your constraint and you're going to include it with the two equations you just created. So what we've done is we've created a little system of equations that we need to go through and solve. Okay, so to solve the system, there's a couple ways you could do it. You could go through and solve the first equation for x, the second equation for y. They'll both be in terms of lambda, and then plug into the third equation. You could solve the first equation for lambda, the second equation for lambda, set those two equal, and then solve for find a relationship between x and y and then plug into the third equation. Both of those two methods that I just described, if you want to go back and listen to it in slow motion, they both work, and we're going to use both of them in different problems depending upon the context of the problem. One is not necessarily better than the other. One might be a little bit easier depending upon the problem. What I'm going to do in this problem is I'm going to go through and I'm going to solve the first equation for x, the second equation for y, and then I'll have x in terms of lambda and y in terms of lambda, and then I'm going to plug into the third equation to solve for lambda. That's just the way that I first thought to do this problem. All right, so what I'm going to do is I'm going to move the 2x over to the other side. We're going to get 3 over 2x equals, hold on, I just did the opposite of what I said I was going to do. We're solving for x, not lambda. All right, so we're going to take the 2 and the lambda, and we're going to divide them over. So we're going to get x equals 3 over 2 lambda. And then we're going to solve for y. We're going to get y equals 1 over 2 lambda. And then I'm going to take those two, I'm going to plug it into the third equation. And so we're going to get 3 over 2 lambda squared plus 1 over 2 lambda squared. And then that needs to equal 10. So we take these two, plug them into the third. Sorry, I got to have arrows all over the place. I'm going to stop drawing arrows, but that's what we're doing. And then we're going to get 9 over 4 lambda squared plus 1 over 4 lambda squared equals 10. That's 10 over 4 lambda squared equals 10. And you could flip both sides. You're going to get 4 lambda squared over 10 equals 1 over 10. Multiply both sides by 10. You get 4 lambda squared equals 1. Then lambda equals plus or minus 1/2. Once I have lambda equals plus or minus 1/2, I'm going to go all the way back to my definitions for x and y, and I'm going to plug those in. So we're going to have lambda equals 1/2. Lambda equals negative 1/2. Those are the two solutions I got. If lambda equals 1/2, we get x equals 3 over 2 times 1/2. That's going to be 3. And we get y equals 1 over 2 times 1/2. That's going to be 1. And then x equals negative 1/2. 2 times negative 1/2 is going to be negative 1. 3 over negative 1, we get negative 3. And then y equals 1 over negative 1. That's negative 1. Okay, and so those are my solutions to the system of equations. Now, a couple comments about the steps that we used here. These are perfect, all right? So we did this correctly. We ended up getting 2 points. We haven't tested them yet, so we're not done. But I just want to comment on something that I did. You notice that I took the lambda and I divided it over to the other side. You can only do this if lambda is not equal to 0. So I assumed that lambda was not equal to 0 in both of these problems when I did this. So can I assume that lambda is not equal to 0? The answer is no, you can't. Why? Because lambda equaling 0 is this third case. This is the case where gradient of f equals lambda gradient of g. And then if lambda equals 0, you get gradient of f equals 0. So that's the case where you ended up going through the peak itself. So you can't go through and assume this just by definition. So what you can do is you can go through and say, all right, I went through and I solved this assuming that lambda was not 0. Let's go back. What happens if lambda is 0? Can lambda equal 0? You don't have to write any of this stuff down. You can just do this in your head. If lambda is 0, what happens? If lambda is 0, you're going to get 3 equals 2 times x times 0. Can 3 equal 0? No. Can 1 equal 0? No. Can lambda equal 0? No. So what we did is perfectly fine. However, what you'll find if we do another problem is that in other problems, it is possible that you could have a lambda equal 0. And so we are going to revisit this in future problems. This second case, where we go through and we say, case 1, we're going to assume that everything works nice. There are no zeros in the denominator. If there are no zeros in the denominator, then it's really a simple problem, and it just kind of follows, naturally the steps that we've drawn here. If we do have a 0 in the denominator, then suddenly it opens up a whole can of worms that we've got to kind of solve and deal with. And I'll show you that in another problem. Okay, anyway, so is this problem done? No, right? So what have we done? We've done all of that was just to do step one, find all the points that satisfy. Then the second part is the easy part. You just need to go through and evaluate the points. So just to keep it on the same page, I'm going to just kind of go up here. So we're going to do f of 3 comma 1. If you do that, you get 3 times 3 plus 1. That equals 10. And then we have f of -3, -1. That's going to be 3 times -3 minus 1. So that's equal to -10. So once you've got your points, the biggest one is the max. The smallest one is the min. And so this is this is the answer over here. That's our answer. Okay, so that's the process that you go through, beginning to end. You start off with your function, you're maximizing or minimizing. You start up and your constraint. Take your constraint, set it equal to g of xy, find the partials, go through and set the pieces of the partials, the derivative with respect to x and the derivative with respect to y, set those equal with this lambda offset. Take the constraint, put it, that's your step one. You've got your system of equations. To solve your system of equations, either solve for x and y or solve for lambda, depending upon the problem. Once you've done that, take your solution, plug it into the third equation, go through and manipulate that until you get lambda. And then once you've got lambda, take that lambda, plug it back into your little solutions that you created here, your little equations that you created here, and that'll get you the x and y. And then finally, you test them. Let's do another one. So we got f of xy equals x e to the y. And then we have x squared plus y squared equals 2. This is the constraint. Take the constraint, set it equal to g of xy. Find the gradient of f. Derivative with respect to x, e to the y. Derivative with respect to y is x e to the y. Find gradient of g, 2xi, 2yj. Set the components equal with a lambda offset. So we're going to have e to the y equals 2x lambda, x e to the y equals 2y lambda. And then don't forget your constraint. This is kind of a step one. We have our system. Step two, solve the system. This time, I'm going to go ahead and I'm going to solve for lambda in both of these two equations, and then I'm going to end up setting them equal. So we're going to do lambda equals e to the y over 2x. And here we're assuming that x is not 0 to do that. We're going to say lambda equals x e to the y over 2y. If we do that, we're assuming that y is not 0. Okay, once I've done that, I'm going to take those two, I'm going to set them equal. So I'm going to get e to the y over 2x equals x e to the y over 2y. So if I go through and cross multiply here, we're going to get 2y e to the y equals 2x squared e to the y. Then we can cancel the 2's. You can cancel the e to the y's, and you get y equals x squared. Once we have y equals x squared, you can plug that in. We're going to get x squared plus x squared squared. So we get x squared plus x to the fourth equals 2. Move everything to one side. Factor, this is x squared plus 2 times x squared minus 1. And there's no solutions to this piece. This piece gives us plus or minus 1. So x equals plus or minus 1. If x equals 1, oops, if x equals 1, what happens? If x equals 1, we get y equals 1 squared, so y equals 1. If x is negative 1, we get y equals negative 1 squared, so y equals 1. And so our points are x equals 1, y equals 1, x equals negative 1, y equals 1. And then over here, kind of off to the side, we will test them. So f of 1, 1 equals 1 times e to the 1, which is e. F of negative 1, 1 equals negative e to the 1, which is negative e. This is the max. This is the min. Just like that. And that's your solution. Okay. There's two examples. One using each of the solving techniques. One where you solve for x and y and then substitute into the third equation, and one where you solve for lambda twice. Oh, whoops, we forgot about the x equals 0, y equals 0. Hold on. Wait, hold on. I jumped the gun there. All right, so what about can x equals 0? Can x equal 0? If I put a 0 here, what happens? Right? Then this whole side becomes 0. Can e to the y equal 0? Is that possible? No. E to the y cannot be 0 no matter what y value we have. Can y equal 0? If you plug in y equals 0, then this becomes 1. That's okay. That could be, we could have, this could be 1, and we could have values for x and lambda that work. How about this equation? Here, if y is 0, then this becomes 1. This becomes 0 on this side, right? If we put a 0 here, you're going to have x times 1 equals 2 times 0 times lambda. So that means x is 0. If y is 0, then x must also be 0. And can x be 0? No, that means that y cannot be 0 either. Okay, did you follow that? Right, so if you just plug values into this, we can kind of do it off to the side here. You're going to have x times e to the 0 equals 2 times 0 times lambda. And so thus, if you just simplify this, this is x times 1 equals 2 times 0. So x equals 0, which we already said is not possible. Sorry, that's supposed to be a 2. It does not look at all like a 2. There we go. All right, so we have to check our the 0 values, and neither one of them can be true. Okay, let's try one where this part that I've been talking about, where that actually matters. All right, how about f of x, y, z? So this one has three variables. That doesn't make it really any different. The process is the same. And then we have x squared plus y squared plus z squared equals 1. This is the constraint. And so the first step you want to do is to say take g of x, y, z and set it equal to that. All right, once we've done that, gradient f, 4x to the third I plus 4y to the third j plus 4z to the third k. Gradient g, 2xi plus 2yj plus 2zk. Set the components equal with a lambda offset. So we're going to have 4x to the third equals 2x lambda. 4y to the third equals 2y lambda. 4z to the third equals 2z lambda. And then x squared plus y squared plus z squared equals 1. So there's our system. All right. So I'm going to use the same technique on this one as I did on the last one. I'm going to solve for lambda in each one of these. So we're going to say that we're going to divide both sides by 2x. And so that means that lambda equals 2x squared. This assumes that x is not 0. Lambda equals 2y squared. We're going to make the same assumption here. Y is not equal to 0. And lambda equals 2z squared. We're going to assume that z is not equal to 0. Okay. Now, if I do that, now we're assuming that all three of these variables cannot be 0. So we need to revisit and check, could they be 0 later on in the problem? However, assuming that they cannot be 0, then what that means is that we get 2x squared equals 2y squared equals 2z squared. Okay, and if that's true, then we can go through and say that x equals plus or minus y, and z equals plus or minus y. I don't know why I chose those two, but it doesn't matter. Just you need to solve for two of the variables. Once you've got x is plus or minus y and z is plus or minus y, you can take those and pop them into the third equation here, and you're going to get y squared plus y squared plus y squared equals 1. So we get 3y squared equals 1, y equals 1/3, and then y equals plus or minus the square root of 1/3. There should be a square here. Plus or minus 1/3. Okay, and so if y is plus or minus 1/3, then you could take that and put it here, and then that means that x could be plus or minus 1/3, and z could be plus or minus the square root of 1/3. And so what that's going to mean, all these plus or minuses, if you go through and break them all down, is it just means that x could be plus or minus 1/3, and y could be plus or minus square root of 1/3, and z, that all the different possible combinations exist, right? The way that you could do this, so you could say, all right, well, let's say y, I'll show you that. So let's say y is positive square root of 1/3. Well, if y is positive square root of 1/3 and x is plus or minus y, then that means that x could be positive 1/3, or x could equal negative square root of 1/3. I don't like writing really small because I'm concerned that people are watching on their phones and they can't really see. Let me write that a little bit bigger. So x equals positive square root of 1/3, or x equals negative square root of 1/3. Right? That's just x. And then z could also be plus or minus, and it's not linked with x. So this creates a second set of circumstances. So z could be square root of 1/3, or z could be negative square root of 1/3. And then the same thing here. Z could be square root of 1/3, or z could be negative square root of 1/3. Now, those are all for the case where y is positive. And you could also have y be negative the square root of 1/3, and then you could have all that same stuff again. So this is just a long explanation for the fact that x, y, and z all can be plus or minus square root of 1/3. So we've got, how many points is that total? That's going to be 8 total points. You can write them out if you want. There's 8 of them. All right. So we've got the points. Now, we're not going to test them yet. Why not? Because we want to go through, this time I intentionally picked a problem where this 0 stuff actually matters here. Now, the question is, can x be 0? What happens if I make x equal to 0? So if x is 0, the left side of this equation is 0. The right side of this equation is 0. That one's totally good. This equation has nothing to do with x. No problem there. This equation, no problem. This equation, if x is 0, it just drops out, and we get y squared plus z squared equals 1. Again, no problem. X definitely can be 0. Yes, this time. And actually, similarly, y could be 0, or z could be 0. So we need to look at those cases and see what happens. So what we're going to do is we're going to say let x equal 0. And we're going to assume that y and z are both not 0. All right, if x is equal to 0, then I just said it. So this equation drops out. And then these three are still good, except you put a 0 where the x is. So we're going to have 4y squared equals 2y lambda, 4z squared equals 2z lambda, and then y squared plus z squared equals 1. Right? And then x is 0. So x is not just gone. It didn't just disappear. X is 0, and then all the rest of this. So from here, you could go through and say, all right, well, lambda is 2y squared, and lambda is 2z squared, and then 2y squared equals 2z squared, and then y equals, or let's be consistent here and solve for z equals plus or minus y. And then you could take that and plug it in, and you're going to get y squared plus y squared equals 1. 2y squared equals 1. Y equals plus or minus the square root of 1/2. Since y is plus or minus the square root of 1/2, z is also equal to the plus or minus the square root of 1/2. And again, it's going to be all the possible combinations, because y could be positive root 1/2, and then z would be plus or minus. Y could be negative, and then z could be plus or minus. So you need all the possible combinations. So what did we end up with for points here? We ended up with 0 plus or minus square root of 1/2 plus or minus square root of 1/2. Now, so that's all assuming x is 0. If x is 0, you've got these two for the other two. What if y is 0 and x and z are not equal 0, right? So just by extrapolation, we can go through and say that we also have plus or minus 1/2 comma 0 comma plus or minus 1/2. That would be the case where y is 0. And then we could go through and have plus or minus 1/2 plus or minus 1/2 0. And that's the case where z equals 0. All right, so you can get all three of these out of by going through and just doing this one and then just extrapolating it. You don't need to go through and write all this out again except with y 0. You don't need to go through and write all this out again except with z equals 0. You can go through and just do them all in one step. Now here's the thing. In this problem, we said that y and z could not be 0, and the consequence was that we got these solutions. What if 2 of the 3 are 0? So yes, we do have to consider that case. Can x be 0? What about can x equals 0 and y equals 0? Can that happen? If x is 0, you get 0 equals 0. If y is 0, you get 0 equals 0. This doesn't have anything to do with x or y. It's still good. Here, the x and the y drop out, and you just get z squared equals 1. So yes, absolutely, you could have 2 of the 3. All right, so let's say we have let x and y both be 0, but z is not equal to 0. In that case, the equation becomes 4z squared equals 2z lambda, and z squared equals 1. So who cares about this equation? This is the only one that matters. This tells us that z equals plus or minus 1. And if you do that, what points did we end up getting? You end up getting 0, 0, plus or minus 1. And then again, by extrapolation, we could say x and z are 0, but y is not. So in that case, you get 0 plus or minus 1, 0. Or you could go through and say that y and z are both 0, but x is not. And if you do that, then you're going to get plus or minus 1, 0, 0. All right, and so we get 3 more possibilities along with the first one, which I guess I just never wrote out the points, but the format for that 8 total points is going to be plus or minus root 1/3, plus or minus root 1/3, plus or minus root 1/3. And that's supposed to be a 3. Sorry, again, I'm writing really small. I don't know what to tell you if you're using a phone. You're trying to read it. I don't know, maybe it's readable. It's just really small because you hold the phone really close to your face. I have to try watching it with a phone and see if I can actually read any of the stuff that I'm writing in here. All right, anyway, so we got 8 points there. How many points do we have here? All right, well, there's going to be 4 points here, 4 points here, 4 points here. So that's 12. 12 more points. And then we've got here 2 and 2 and 2. Here's 6 more points. And so we need to go through and test all these points. So let's do that. All right, so to test them, how do you test them, right? How do you test these points? You plug them back into the original function. All right, the biggest is going to be the max and the smallest is going to be the min. So we're going to have, let's just do them kind of all at once. We're 4 plus or minus root 1/3, plus or minus root 1/3, plus or minus root 1/3. What's going to happen here? We're going to get root 1/3 to the 4th plus root 1/3 to the 4th plus root 1/3 to the 4th. I'm ignoring the plus or minus here because the 4th power is just going to get rid of the sign. And then if you do that, you're going to get root 1/3 times root 1/3 is 1/3 times another 1/3. So we're going to get 1/9 plus 1/9 plus 1/9 equals 1/3. All right. Next, what about this? The next group. So we have, what were those? So these 12 possibilities. So we're going to have plus or minus root 1/2. Let's not root 1/3, 1/2. Plus or minus root 1/2, comma 0. That's going to equal f of plus or minus root 1/2. Oh, did it again. Got 1/3 on the brain. Comma 0, comma plus or minus root 1/2. That's going to equal 0, comma plus or minus root 1/2, plus or minus root 1/2. And all of that equals root 1/2 squared, not squared, 4th. Yeesh. The 4th plus root 1/2 to the 4th. This is root 1/2 times root 1/2 is 1/2. 1/2 times 1/2 is 1/4. So we get 1/4 plus 1/4. That equals 1/2. And finally, f of plus or minus 1, comma 0, comma 0 equals f of 0, comma plus or minus 1, comma 0 equals f of 0, 0 plus or minus 1 equals just 1 squared, and you get 1. All right, so all of these 8 points, that's our smallest output. These are all minimums. All 8 of them. And these 6 points are all maximums. All 6 of them. And that's the answer. It's really big to box. I'm going to try it anyway. Box it all. That the whole thing is the answer. All right. Okay, so that is the lesson on Lagrange multipliers. Thank you for watching. I will see you next time.